welcome everyone. Today we are going to start a very important topic in our database course, functional dependencies. This topic lies at the heart of good database design. It helps us understand how data items in a table are related to each other and how we can organize our database structure to avoid redundancy, maintain consistency, and improve database integrity. In this lecture, we are going to discuss one of the most fundamental concepts in relational database design, that is functional dependencies, and how they form the foundation for normalization. Functional dependencies play a key role in differentiating good database design from bad database designs. When we say a database design is good, we mean it avoids problems like redundancy, inconsistency, and update anomalies. And that's exactly what functional dependencies help us achieve. Now, what exactly is a functional dependency? A functional dependency is a type of constraint that expresses a relationship between two sets of attributes in a relation. It tells us how one attribute depends on another. Formally, we say that an attribute y is functionally dependent on another attribute x. For every value of x, there is exactly one corresponding value of y. We usually write this as x to y, and we read as x determines y. You can think of it as a generalization of the concept of a key. Key is simply a special case of a functional dependency. It's the minimal set of attributes that uniquely identify all other attributes in a table. Now let's take a closer look at some basic terminologies related to functional dependencies. First, x is called a determinant, and determinant is simply an attribute or a set of attributes that uniquely determines another attribute or group of attributes. So when we say x determines y, we mean that for every value of x, there is one and only one corresponding value of y. In other words, y is functionally dependent on x. This relationship is denoted by the arrow notation x to y. We read it as x determines y. This is the standard way of expressing a functional dependency in database theory. Sometimes we came across what are called trivial dependencies. A dependency x to y is said to be trivial if y is a subset of x. That means if the attributes on the right hand side are already included in x, then the dependency does not add any new information. It's automatically true. For example, if x consists of attributes student ID, name, then the dependency student ID name should be dependent upon name is trivial because name is already part of x. Understanding this distribution between trivial and non-trivial dependencies helps when we analyze database schemas, especially in the process of normalization, where we try to simplify tables while preserving these dependencies. Now let's move toward the formal definition of a functional dependency. A functional dependency written as x determines y is said to be satisfied in a relation instance or of a relation R if the following condition holds. For every pair of tuple, let's say t and s in the relation R, if t and s have the same values for all attributes in x, then they must also have the same values for all attributes in y. In similar words, whenever two rows agree on x, they must also agree on y. This is what it means for x to determine y. The value of x uniquely identifies the value of y. Suppose we have a relation student, its attributes roll number, name, department, and advisor. If we say name is dependent upon name, department, and advisor is dependent upon roll number, it means that whenever two tuples have the same roll number, they must also have the same name, same department, and same advisor. If that condition holds true for all pair of tuples in the table, then the functional dependency is said to be satisfied in that relation instance. This formal definition is very important because it provides the foundation for checking whether our database design obeys the intended dependency, something we will use later during normalization. Now that we understand what a functional dependency is, let's see how key constraints are actually a special case of functional dependencies. Remember, a functional dependency expresses how one set of attributes determine another set. A key constraint is a specific kind of functional dependency. In other words, when a particular set of attributes, say X, determines every other attribute in the relation, we call X a key of that relation. Formally, we can write this as X determines all attributes of R. That means knowing the value of X is enough to uniquely identify every other attribute in the table. Let's take an example. Suppose we have a relation student having attributes roll number, name, department, and advisor. Roll number determines every other attribute, name, department, and advisor. Then we can write roll number that is determined upon name, department, and advisor. Here roll number is a key because it uniquely identifies all other information about a student. So key constraints are simply functional dependencies that are maximally determining, meaning nothing more in the table can be determined beyond what's already covered by that key. This connection between functional dependencies and keys is crucial because when we perform normalization, we often use these key-based dependencies to decide how to split or combine relations in a logical way. Now let's talk about the concept of an irreducible set of functional dependencies, sometimes also called a minimal cover or canonical cover. When we work with functional dependencies, it's often useful to simplify or minimize them to find an equivalent set that contains no redundancy. The resulting smallest possible form is called an irreducible or minimal set of functional dependencies. Formally, a set of dependencies S is said to be irreducible if it satisfies three important properties. First, each functional dependency in S must have only one attribute on the right hand side. That means if we have a dependency like BC, A determine BC, it means we should split it into two separate dependencies, A determines B and A determines C. This makes each dependency more atomic and easier to analyze. Second, each left hand side must be irreducible. This means we can't remove any attribute from the left hand side without changing the meaning of the dependency. Now we will discuss one of the most important foundation concept in functional dependency theory, that's Armstrong axioms. Armstrong axioms are set of inference rules that allows us to derive all possible functional dependencies implied by a given set of dependencies. They form the theoretical basis for reasoning about dependencies during normalization. The first of these axioms is the subset property, also called the axiom of reflexibility. It states that if Y is a subset of X, then X functionally determines Y, written as X determines Y. This means that any set of attributes automatically determines its own subsets because they already contain that information. The second rule is the axiom of augmentation. It states that if a functional dependency X determines Y holds, then adding the same set of attributes G to both sides of the dependency will also hold true. Formally, if X determines Y, then Xg determines Yz. In simple terms, this means that if knowing X determines Y, then knowing X along with some extra information Z will still determine Y along with Z. Let's look at an example. Suppose we know that roll number determines name in a student table. If we now add another attribute, say course, to both sides, we get roll number and course determine name and course, and that's still valid. This property allows us to extend dependencies by including additional attributes without breaking the relationship. The third rule is the axiom of transitivity. This one is quite intuitive. It states that if x determines y and y determines z, then x must also determine z. In formal terms, if x determines y and y determines z, then x determines z. This rule is similar to the transitive property we know from math. If A leads to B and B leads to C, then A also leads to C. We have covered the three primary Armstrong axioms: reflexivity, augmentation, and transitivity. Let's look at some secondary or derived rules. These additional rules can actually be derived using the primary axiom, and they make reasoning about functional dependencies much easier in practice. The first derived rule is the union rule. It states that if x determines y and y also determines z, then x determines both y and z together. In formal notation, we can say if x determines y and y x determines z, then x determines both y z. For example, if we know that roll number determines name and roll number determines department, then we can combine them to say roll number determines name and department. This rule helps us merge multiple dependencies that share the same determinant. Formally, if x determines y z, then x also determines y and x also determines z. This rule is very useful when we want to break a complex dependency into smaller, simpler parts, especially when analyzing or normalizing a schema. The third derived rule is pseudo-transitivity. It extends the idea of transitivity by involving an extra attribute set. It says if x determines y and omega y determines z, then combining x and omega will determine z. Now we have learned how functional dependencies work and how to infer new ones using Armstrong axiom. Let's talk about a very important concept, the closure of a set of functional dependencies. The closure can be thought of as the complete set of attributes or dependencies that can be determined based on what we already know. In simpler terms, closure tells us everything that can be logically derived from a given set of functional dependencies. When we compute the closure, we are essentially exploring the full consequences of the dependencies defined in our relation. We use Armstrong's axiom as the proof of mechanism to derive all possible dependencies. So closure is like asking, given the dependencies we know, what else can we logically conclude? Understanding closure is crucial because it helps us to identify keys of a relation. Test if a decomposition is lossless and check whether a dependency is redundant or implied by others. Formally, let's define what we mean by closure. Suppose we have a relation R and a set of functional dependencies F that hold in R. The closure of F, denoted as F plus, is defined as the set of all functional dependencies. The closure of F, denoted as F plus, is defined as the set of all functional dependencies that can be logically implied by F. In other words, F plus includes all the dependencies explicitly listed in F and all the dependencies that can be inferred from F using Armstrong rules. So when we compute F plus, we are discovering every dependency that is true according to the logic of F. Particularly, we can say this helps database designers to reason about whether certain dependencies are redundant or implied. So far, we have discussed the closure of a set of functional dependencies, but in practice, we often need the closure of a particular set of attributes called the attribute closure. The attribute closure, denoted as X plus, represents all the attributes that can be functionally determined from a given attribute set X using the dependencies in F. Here is how we find X plus step by step. Start by initializing X plus with all the attributes in X itself. Then for every functional dependency y determines z in f if f is already contained within x plus. We add z to x plus because it means x can determine z through y. We can repeating this process until no new attributes can be added. Once we reach that point, x plus contains every attribute that x can determine based on the given dependencies. This concept is extremely useful in database design. For example, to check whether x is a candidate key, x plus include all attributes of R. Then x is a key for that relation. So attribute closure is not just theoretical, it's a practical tool that helps us to design better normalized database schemas. Now define the closure of an attribute set denoted as alpha plus. Suppose we have a relation R and a set of functional dependencies F. The closure of alpha under F written as alpha plus is the set of all attributes in R that can be functionally determined from alpha using the dependencies in F. In other words, alpha plus tells us everything that can be derived from alpha based on the given functional dependencies. We will use this concept often to identify keys and analyze dependencies. Computing alpha plus is very useful in practice. First, if the closure of alpha includes all attributes of R, that is alpha plus is equal to R, then alpha is a super key. Second, by finding the closure for every subset of attributes in R, we can determine F plus the complete set of all implied functional dependencies. So alpha plus help us to test keys and understand the overall dependency structure of a relation. Here is a simple algorithm to compute alpha plus. We start with result is equal to alpha, then repeatedly apply all functional dependencies for each dependency if beta that is dependent. If beta is already contained in our result, we add it to y. We keep repeating this process until no new attribute can be added. That's when result is always temporary. So this method is the foundation for checking super keys and normalization conditions in database design. That's all for today. We will discuss normalization in our coming lecture. Thank you so much. Allah Hafiz.